Hi everyone! Your favorite video games, the cryptocurrency market, and the most advanced AI models. What do they all have in common? They're all powered by the magic of the GPU. But how did a device designed for graphics become such a force for innovation? Keep watching as we dive into the incredible story of GPUs. This video has 3 parts: how GPUs evolved, booming GPU demand, and GPUs as accelerators. Part 1. How GPUs evolved. The original GPUs evolved out of a need to put pictures on computer monitors. They were very basic at first, displaying just enough information for text consoles in monochrome or maybe 4 colors at most. There were several standards along the way, but the most famous is the VGA standard. Even today, you'll see VGA used frequently to talk about a graphics card, for example, in the Linux command line that lets you configure your GPU. The very first computer games that I made were actually targeting the VGA standard. I used a mode called 13H, which had 320 pixels by 200 pixels, which is, of course, absolutely tiny by today's standards. Each of those pixels could be set to one of 256 different colors, and you could set the palette, but that was basically it. And you had to worry about really low-level details such as double buffering. But let me take a step back for a moment. A GPU has inside it a bunch of memory that represents the different pixel values that are supposed to be displayed on the screen. Whenever the monitor wants to refresh and figure out what color pixel should be here, it goes into the GPU and checks the value of that memory cell. So you have the equivalent of all the pixels on the screen just laid out there in memory. The problem is that monitors just refresh on their own. The original monitors, remember, were CRT based, and they would have a 50 or a 60 hertz refresh rate, just like old school televisions. What this meant was that the monitor would actually go and refresh or draw each line of pixels on the screen in a kind of top to bottom manner. And as it was drawing a single line, it would actually read those memory cells and figure out what to put on the screen. And again, because it was a CRT, it would be doing this about 60 times per second, just putting on the screen whatever happened to be in memory. There's one problem with this, which is that if you have a program like a game that's actually writing to that memory, trying to display something different on the screen, right as the monitor decides to start a new sweep, and then it starts painting information that's only partially constructed. So some programs would wait for a so-called vertical sync, which is when the CRT would actually go back to the top and start its new scan, and only then start filling in the information for the next frame of graphics. But you had to be really fast, right? You had to put those pixels in place in less than 1/60th of a second, because otherwise you would get half of one frame and half of the next, and you get this flickering effect on the monitor. So the other way to solve that problem, if your program can't run fast enough, or if you actually want it to run faster than 60 frames per second, is you actually have 2 buffers. One of them is whatever the computer monitor is currently displaying, and the other is where you're creating the next frame. And then when you're done, you just tell the monitor, look, this is now the memory that you should be looking at. And now this is your other buffer that you can go and scratch around and make the new frame. So you're constantly switching back and forth between these buffers. And that is actually how most games in the DOS era actually worked. They implemented their own double buffering system in order to mitigate potentially slow graphics cards or potentially slow CPUs. Of course, not all graphics cards at the time had enough memory to store every pixel twice. Early GPUs were extremely memory constrained, which meant that they were very resolution constrained as well. But as the generations progressed, you got higher and higher resolutions, and pretty soon way more memory than was actually needed for just one set of pixels on the screen. GPUs also ended up using the fastest memory available, often much faster than the main memory that the CPU would use. Because for a GPU, everything is about speed. To be clear, we're not talking about anything 3D here at all. We're just talking about a very simple 2D way of displaying pixels on the screen. I made a lot of DOS games in this kind of mode. I want to highlight one as just an example, which was a star cluster simulation. It had a bunch of different stars, and it would emulate gravity and pull the stars to each other, and it would get some interesting patterns. Anyway, that sounds 3D, and it was, because all I did was take the 3D calculations and do them myself. It's actually extremely easy. Let's say you have the X coordinate and the Y coordinate, and that just corresponds to somewhere on the screen. Now you have this Z coordinate, which corresponds to some distance into the computer monitor. And all you do is you take the X coordinate and divide it by Z, and you take the Y coordinate and you divide it by Z. If you do that, you get very basic 3D effects. This section will be a bit technical, but it's sort of standalone, so if you don't get any of it, you can just skip ahead to the next section. The next stage of GPU evolution was so-called fixed pipeline 3D rendering. So when 3D graphics were first happening, you had everything drawn with triangles. You would establish a set of triangles, hand it to the GPU, and the GPU would figure out what all the individual pixels were going to be. In addition to triangles, the other main thing you have is light sources, and depending on whether the triangles are actually facing the light source or not, you would get different amounts of brightness on the triangles. And all this is called the fixed function pipeline, because a lot of it was hard-coded into the GPU. In order to get everything to actually run fast enough, remember 60 frames per second, the GPU had to implement almost all of this in hardware. This is when DirectX and OpenGL were introduced. Those were two different standards. DirectX was the Microsoft one, and everyone else used OpenGL. They were two ways of describing to a GPU, to the hardware, exactly what you wanted to draw. Pretty soon after the fixed function pipeline, GPUs started to evolve the programmable pipeline, where basically the hardware started getting fast enough that it wouldn't just always use one lighting model, for example. You could send it little bits of code, which were called shaders, and the shaders would describe how the lighting was going to work. Originally, you could have one shader per vertex of the triangles. So if you had an object with a dozen triangles on it, you'd have something like 10, 20, 30 vertices, and each vertex would have a little program associated with it called the vertex shader. And then the GPU would just interpolate between the corners of the triangle when figuring out the color of the pixels in the middle of the triangle. Later, as they got even faster, you started to have pixel shaders, which were incredible because you had one piece of code for each pixel. If you had a triangle, you could actually have different lighting effects in the middle of the triangle. You wouldn't just have a smooth gradient between the three corners of the triangle. Of course, all of this was directed by DirectX and by OpenGL, although they had two different programming languages for shaders. Again, Microsoft did all it could to maintain DirectX as an incompatible standard with OpenGL. That's how Microsoft maintained Windows as the prominent platform for PC gaming. Before we leave the programmable pipeline, I just want to mention textures, which are basically images that you could use to put onto a triangle, for example. Textures were actually super powerful, and you can do things like environment mapping and bump mapping, like minor 3D effects on the surface of a triangle. And of course, you can have really high resolution, really cool looking images on your 3D objects. And textures are what really pushed GPUs to start having lots and lots of video memory, because there's only so many pixels on a screen, and if memory was only used to represent those pixels, well, you wouldn't really need much memory in a GPU at all. But once you start having textures, you want 2 megabytes, 10 megabytes, a gigabyte, 8 gigabytes, however much memory you can get your hands on, so that you can store lots and lots of different assets in the GPU memory where it's really fast to access them at any time, from the shaders, of course. Since the RTX 2080 generation or so, GPUs have started to get Raytracing abilities built into the hardware as well, and they're constantly doing fancier and fancier effects. But that's the basic idea. Originally a fixed pipeline, then a programmable pipeline, where there's little shaders, which are individual programs that are running on every vertex or every pixel. And the shaders are allowed to access textures as if they're big 2D arrays, or 3D arrays, or multidimensional arrays, and mix it all together and you get cool effects. Part 2. Booming GPU demand. So GPUs were originally for graphics, and then what happened was they got more and more programmable as the hardware became more capable, and actually they became generic enough to solve many problems beyond just graphics. If you look at the NVidia stock price, for example, well, their original focus was on gaming, and then you can probably see where cryptocurrencies really started to take off because everyone wanted their hands on a GPU at that point. And then again, more recently, when AI really started to take off and everyone wants GPUs for AI training. I guess you could say I was slightly ahead of the curve because when the crypto boom was happening, I actually wanted to get my hands on some GPUs so that I could use them to train models for speech recognition. First, I borrowed some K40 GPUs from my lab, which are pretty outdated GPUs, and I tried to put them inside some computer cases until I realized that only certain motherboards were compatible with those K40 series GPUs. So eventually I went onto eBay and I ended up buying 2 GPUs, 2 1080 GPUs for a pretty good price, and once they were shipped to me, they smelled so strongly of burned electronics that you could tell that these GPUs had been running at some unhealthily high temperature, like 99 degrees or something. That's Celsius, I'm Canadian. Burning electricity in some crypto mining farm. They'd probably been used for a year or two, and then the owner had decided to upgrade and get some better cards for Bitcoin mining. So they were cheap, but I didn't care. I just upgraded the power supplies in some computers in the lab, threw the GPUs in, and with a bit more configuration, I had 2 working systems with powerful GPUs. I plugged everything into this industrial-sized outlet, let it all run, and when I actually fired it all up and I had all the CPUs and GPUs running, I would actually blow out the power adapter by drawing more than 1.4 kilowatts, and all the computers would shut down and I'd have to go and turn them all on again. Anyway, it was tons of fun, but there are a lot of details to get right when you're trying to run your own GPU computing cluster. That's why a lot of people use GPUs in the cloud, because if you can just rent GPUs, why go to all the trouble of trying to maintain them yourself? There's just one problem. NVIDIA basically has a monopoly on the high-end GPUs. I'll talk more about that in a moment, but in order to prevent NVIDIA from competing against itself, it actually artificially split the GPU market into a few segments. Broadly, these segments are consumer GPUs for gamers, workstation GPUs for high-end computers, GPUs, and data center GPUs that can really only be used in servers with a data center license. Remember I said I tried to get some K40 GPUs and just put them in my computer and hoped it would work? The reason it didn't is that K40 GPUs are data center GPUs, and I was trying to put them into a workstation, and they were not compatible, so NVIDIA prohibits that from actually running. You might be able to guess why they do this. Basically, they charge an arm and a leg for those data center GPUs. The workstation GPUs are also sky-high expensive, and then they try to make their gaming GPUs as cheap as possible because that's more of a consumer market. But something really funny happened around the 1000 or 2000 RTX series. Their consumer GPUs became so good that they actually ended up outperforming the workstation GPUs and even started to approach what the data center GPUs were capable of. So everybody was actually putting together their own systems with these gaming GPUs inside them because that was actually the highest performance that you could get at the time. Of course, you couldn't put them inside a data center because that would be violating NVIDIA's terms of service. But what you could do is pay for and assemble like 8 of your own computers and put 8 GPUs inside each one, and you're off to the races. Anyway, long story short, it's almost always extremely expensive to rent GPUs in the cloud. And the root cause of this is NVIDIA's own pricing model. They make a lot of money from it, but it makes everyone else's lives pretty difficult. It's so expensive, in fact, that people rent their own GPUs, and there are companies that are not a cloud service that get the consumer GPUs and sell them in what is essentially a cloud service. But those companies are pretty small because if they get too big, they'll run afoul of NVIDIA. To give you an idea of how expensive, at one point when I was considering assembling a new computer for a GPU, it would have ended up paying for itself in 2 months. 2 months of cloud computing GPU rental would pay for the entire computer and the purchase cost of the GPU. That was an extreme example because I wasn't paying for electricity in that case, and GPU prices were also inflated because of the crypto boom. But if you know that you're going to be using GPUs for any length of time, it's usually more cost effective to actually get those machines physically yourself in a co-location area or something. This doesn't generally hold for all computers, right? It's generally much more flexible and much easier to actually rent CPUs and regular servers in the cloud. But GPUs are another story. Part 3. GPUs as accelerators. As I mentioned, GPUs, although they were originally designed for graphics, ended up becoming generic enough that you could use them to solve a lot of different problems. And what happened was this shader language that used to describe the program to run on every pixel, for example, ended up becoming a general purpose computing language. Actually, several languages. I don't know all of them, but you have like OpenGL and Cuda is the main one that was used on NVIDIA GPUs. So why would you do all this? You already have a CPU that can run any program at all. Why would you go to the GPU to try to solve some crypto problems or some AI problems? Well, the answer is that GPUs had to solve one fundamental problem. They wanted the same code or nearly the same code running tons and tons of times in parallel because most pixels, or at least the pixels in the same triangle, would have the same shader associated with them. So a GPU ended up being massively parallel computation as long as you're running the same computation on a bunch of different inputs. To give you an idea of how parallel, it's not uncommon for a GPU to have, say, 1,000 or even 5,000 Cuda cores. And each of those Cuda cores is running a Cuda program. Now, you can usually only have a few different Cuda programs running at once, but if you actually have the same computation to be done across a lot of different places, you can actually have 5,000 cores running at once, for example, which is a lot more cores than you can get in a regular CPU. It comes with a lot of restrictions, though, even once you have that general purpose programming language like Cuda. Cuda programs can't have loops. They can't really have if statements. Actually, they can have if statements, but the way it's implemented is you have, say, 1,000 copies of the program running, and then a few of them hit the if statement, and you just kill the execution of the ones that fail the if statement. So you start with 1,000 of them running, and then you go, oops, 200 of these ended up taking the if the wrong way, we'll just kill them and keep running the other 800 copies. Keep in mind that although a GPU is basically like a little computer all on its own, it has its own memory, it has its own CPU cores, it's way too specialized to actually act on its own. If you can't have loops and you can't even really have if statements, you're going to have a hard time doing much of use. That's why the CPU is always still involved whenever you have a computer with a GPU in it. For example, if you're doing AI stuff and you're running PyTorch, for example, PyTorch is just a Python program and it's running on the CPU and it's making periodic calls to the GPU to say, please run this computation. Okay, here's some data, ready, set, go. Some of those ideas from GPUs even ended up into CPU design itself. For example, modern CPUs actually have what are called SIMD instructions, single instruction, multiple data. And that usually means one instruction where you're doing the same operation across, say, 4 different data elements or maybe 8 different data elements. But because it's a CPU, these SIMD instructions are very generic, just generic vector operations. But they still let you get a 4x or 8x speed up on certain operations like video decoding or hash computation. So it's very interesting to see. You have CPUs that are designed to run any program at all, and as a consequence, their CPU cores are quite complicated and you can only have so many of them. And you have GPUs that are designed for massively parallel computations, originally just per pixel or per vertex computations. But eventually GPUs started to get generic enough that they could have if statements, and CPUs started to get specialized enough that they could have SIMD instructions. So they're both sort of starting to meet in the middle a little bit, but the ultimate purpose of a CPU and a GPU is very different. So why are we using GPUs for everything? The main reason is a matter of scale. It's very expensive to do the research and development, let alone the production of specialized hardware accelerators. There are tons of hardware accelerators out there, but most of them are not mainstream at all. GPUs only became mainstream because people liked games enough that they were willing to pay a significant premium to get that hardware necessary to do really cool graphics. And then computers started getting built around the idea of having a GPU in them. For example, motherboards have what are called PCIe slots, which is basically just the connection that a GPU can slot into. And it's all very standardized. Lots of different GPU manufacturers can all fit the same thing, as can other peripherals. But again, nothing has the money and the research behind it that GPUs did. This connection, by the way, the PCIe connection, you can have an X1 all the way up to an X16 in terms of how much data can be transferred at once. X16 is 16 times the amount of data. It's so specialized that most CPUs can't even really handle much more than one X16 at once. If you put in 2 GPUs, they're probably going to be X8s. If you put in 4 or more GPUs, they might even be X1s. And that really slows down the communication between the CPU and the GPU. So it's all pretty modular depending on if you want really fast communication or you want more GPUs in the system. So once GPUs became general purpose compute, why not? As long as you have a problem that looks kind of similar to graphics, like you have a bunch of problems that you all want to solve in parallel with basically the same code in each case. And it turns out that if a CPU can't solve a problem, it's probably because the problem is really large and you need a lot of computational power to do it. So GPU is a natural fit. So let's talk about a couple of the applications. For graphics, this bandwidth, the speed between the GPU and the CPU is actually really important because games are usually constantly loading new textures into the GPU's memory when you enter a new area of the game, for example. So the slower that connection, the longer you have to wait in loading time. For cryptocurrencies, they're going to be running that GPU as fast as possible all the time, and the GPU clock speed is actually what's important. Very little memory is needed. You're just trying to get the GPU for that computational ability, which can be parallelized, otherwise you wouldn't be using the GPU. But it's really like a computation-bound thing. And actually, some cryptocurrency designers started using some algorithms that actually required lots of memory in order to prevent people from actually using a GPU to solve that problem. If you need too much memory, then it might not actually fit on the GPU, and you can't really use that like really efficient brute forcing method that you can use on Bitcoin, for example. Finally, for AI, the total amount of memory space is actually what's most important. And this applies for both training and inference. The reason is that when you're doing deep learning, you end up putting all the model weights into the GPU's memory. Remember, the GPU memory is usually even faster than the main computer's memory. When computers were using DDR4 for their main memory, GPUs were already using GDDR5. And even when you have a fast connection between the CPU and the GPU, you don't want to be constantly transferring model weights back and forth if you can help it. So in AI, when you're training, you put the current model weights inside the GPU's memory, or potentially split across the memory of lots of GPUs, and you start feeding it different data points, actually probably many data points at once, and it will take that input and incorporate it into the model weights. Then later, when you're doing inference, you just load the model weights one time, read only, and again, you start doing inference on multiple data points at once if you want to, and you get the answers out of the GPU. So GPUs served as a kind of general purpose accelerator for crypto and for AI. Of course, once a market becomes big enough, you would end up creating special purpose accelerators for the different problems. For cryptocurrencies, for example, everyone was mining Bitcoin on GPUs until some people realized that if you used an FPGA, like a programmable piece of hardware, you could get it to run faster than on a regular GPU. And then eventually people even made ASICs, which are like hard-coded hardware, the same way that a GPU specifies very precisely in its circuits the only thing that it can do. You end up creating a special purpose circuit whose sole ability is to do the hash computations needed for Bitcoin. Even by about 2017 or 2018, which I think is when I got my first hardware Bitcoin miner, it was already an ASIC by that point. When you talk about AI, GPUs have been extremely successful, not the least because for really large AI models, you actually need to build basically a supercomputer or a cluster of a lot of machines in order to have a lot of GPU and a lot of computing power. And that's really complicated, but since you can hook up GPUs to relatively standard motherboards and computer equipment and then use relatively standard computer networking, you're kind of just standard all the way, and it makes it easier to build those larger clusters. But we're already starting to see AI accelerators. NVidia hasn't really made one yet. They're just sticking on this path of everything is a GPU, but Google made the TPU, the tensor processing units, and those are basically special purpose AI chips. What do you need for AI? Well, we already know that you need lots of memory. You need the ability to do lots of matrix multiplications and similar transformations, which by the way are basically called tensors, which is why it's called the tensor processing unit. But importantly, you actually don't need really accurate floating point numbers. You can actually use what are called half precision floating point numbers, and you still get calculations that are good enough for AI. So that's basically what the TPU does. And it's the same as what Google put into their Pixel phones, Pixel 6 and newer. Those phones have a little bit of special purpose hardware that's actually designed to execute AI models. It's like a really mini TPU. And interestingly to me, that's actually in addition to the GPU that's present on those phones. Because phones do a lot of graphics stuff, they still have a GPU, but it was probably more power efficient and definitely faster to actually put some special purpose hardware in there that's only designed for running AI models. They do use it for speech recognition, but you don't really need anything too powerful for that. The main thing is for doing image manipulation like the magic eraser stuff and whatnot. That would be pretty hard to do, at least on the device, without having access to some hardware. Will we see even more AI accelerators in the future? I know there's some startups that are trying to do graph-based computations in hardware, which would be a leg up. You could get away with doing lots of computations without having to load and then reload the GPU's memory. But honestly, I think it depends on whatever NVIDIA wants to do. They already gave a little and implemented the half precision floating point numbers in all their recent GPUs so that you could have effectively twice the memory, which of course is really good for AI. But NVIDIA has such a stranglehold on the market because that whole stack from the Cuda to the stuff on top of it like PyTorch is really hard to replicate. So maybe NVIDIA will stay in the everything is a GPU bandwagon, or maybe eventually they'll start having more special purpose AI chips. It'll be very interesting to see what those look like. Finally, in conclusion, I talked a lot in way too much detail about graphics and about how GPUs evolved from the very early stages and how they eventually got more and more sophisticated, more and more programmable with tons and tons of really fast memory inside them. And that made them ideal for lots of accelerated computations in various domains from crypto to AI, amongst others. The current gold standard is to use Cuda, which is the general purpose computing language for NVIDIA cards. And again, people don't really write Cuda directly. They use other platforms that generate the Cuda, usually running on the CPU to control the GPU. And long story short, in the case of crypto, they quickly moved to faster and faster accelerators because the computations are relatively simple and they didn't need the memory. But for AI, the memory is actually one of the most important things. So once you have those half precision numbers that AI likes, and you can fit a model that's effectively twice as big into that memory, a GPU is already almost ideal. Again, every GPU still has inside it the original fixed function pipeline and the newer programmable pipeline with all the shaders and all the previous versions of OpenGL and all the previous versions of DirectX. So you can save a little bit of overhead if you wanted to drop all of that and say this is an AI chip only. But so far, NVIDIA hasn't, presumably because there are relatively minor gains to be had there. By the way, the only reason Google did, I think, is because they have their entire own stack, a separate stack, right? They all use TensorFlow instead of PyTorch, and they really wanted to double down onto being an AI company. So they probably liked not having to pay NVIDIA prices for all of their training hardware. Anyway, I hope you learned a thing or two about GPUs. If you liked this video, check out this previous video I made about another type of accelerator that has the potential to really transform computing, and that is quantum computers. They're the same sort of thing. Special purpose, really good at solving certain problems, probably best used in conjunction with a CPU. Anyway, don't forget to like and subscribe. That's all I have for today. Thank you very much for watching. Bye.